Good morning, students. Today, let us see directed acyclic graph. Okay. So already we have seen about the syntax tree, right? Today we will see the common sub-expression elimination or reducing the syntax tree. That is our DAG. Let me share the slide. Okay. So in our compiler design, in the phases of compiler, DAG comes in our code optimization, right? So let us see about DAG, that is directed acyclic graph, which is one of the important concepts in our code optimization. I am Dr. A.K. Jaitanvi, Assistant Professor, Department of Computer Science and Engineering, RMD Engineering College. I have in total 20 years of experience, and in our college, RMD, I have been working for the past 12 years. Let us come to the topic, right? Directed acyclic graph. So by this word, what do you understand? There should not be any cycle. That is directed acyclic graph, right? Right. So in compiler design, a directed acyclic graph DAG is on abstract syntax tree with a unique node for each value. Okay. So it is an abstract syntax tree, or it can also be said as directed graph that contains no cycle. So it is acyclic means that there is no cycle. Okay, now what is the purpose of this DAG? So it is used in our code optimization to reduce the size of the code, thereby improving the running time complexity. Now, DAG is useful data structure for implementing transformation on basic blocks. A basic block can be optimized by the construction of the DAG. A DAG can be constructed for a block, and certain transformations such as common sub-expression elimination, dead code elimination is applied for performance of the local optimization. To apply the transformation on the basic block, a DAG is constructed from the three address code. So in the previous class, we have seen about the three address code as one of the intermediate representation of our ICG, intermediate code generator, which is the fourth phase of the compiler. Now, let us see what is the application of this DAG. So it is to determine the common sub-expression. Otherwise, we can eliminate the common sub-expression. Determine which names are used in block and computed outside the block. Determine which statements of the block could their computed value. Now, what is the rules for constructing this DAG? So if you see the diagram there, I stands for the intermediate node, L stands for the leaf node. We are supposed to follow these rules. Rule 1, in a directed acyclic graph, leaf node represent identifiers, names or constant. Interior node represents the operators. While constructing DAG, there is a check made to find if there is an existing node with the same children. A new node is created only such a node doesn't exist. Okay. If the meaning of this is already if a node exists, right? In that case, we are not supposed to create a new node. We'll be using the already existing node. Right. Now, this action allows us to detect common sub-expression and eliminate the recomputation of the same. The rule 3 is the assignment of the form x is equal to must not be performed until and unless it is a must. Right? Unnecessary assignment should not be performed. Let us see the first example for constructing the DAG. A plus B star, A plus B plus C. So as you all know, the three address code is T1 is equal to A plus B, right? Then T2 is equal to T1 plus C. Then T3 is equal to T1 into T2. This is an optimized code, right? Now, how to construct the DAG for this, right? So you will create a node for A, node for B, and you will add it, that is A plus B, right? So the intermediate value, the temporary is used is T1 for it. Now next is, once again you have A plus B, we are not creating it since it already exists. Now we find C, so you create a node. Now you need to add A plus B, right? You need to add to this A plus B, right, this C, right? So you will be adding it and finally you will be multiplying it, okay, right? So this is your DAG. From the constructed DAG, we observe that the common sub-expression a plus b is translated into a single node in the DAG. The computation is carried out only once and stored in the identifier P1, and once again it is reused. This illustrates how the DAG construction scheme identifies a common sub-expression and helps in elimination its recomputation later. Let us see the problem 2, a plus a, right? So you are adding this a plus a 4 times. Okay, so just that too, it is not a plus b, it is a single operand. So we create only one node for that a. So you are saying a plus a. This is once again added to itself and once again added to itself. So you are adding a plus a, then the second plus here represents that it is you are adding a plus a plus a plus a, and this represents that you are adding this a plus a plus a plus a 2 times. You understood? So this is a plus a. Up to this is a plus a plus a plus a. So this plus is for what? Your left side will be a plus a plus a plus a, and right side will be a plus a plus a plus a. Next, we can see for this expression, right? A is equal to B into C, D is equal to B, E is equal to D into C, B is equal to E, F is equal to B plus C, G is equal to F plus D. Now, first you multiply B and C, right? So for assigning that B to D, we'll just put the comma operator. So the major rule is what? The third rule is we'll be avoiding the unnecessary assignment, right? Now next is you are multiplying only once again the D into C, right? So it will be set as A comma E. Then once again you are assigning it to B. Then you are adding it, right? Finally you are adding once again F plus D. So you can find these steps. So this is a simplified representation of your syntax tree where we get the optimized code, thereby reducing the time consumption. Thank you, students.